Let's continue our discussion of CAM design by first starting again with the fundamental law of CAM design and its corollary. What we have for the fundamental law of CAM design is as follows. A CAM function must be continuous to the first and second derivatives of displacement across the entire interval. That's 360 degrees. And the corollary of that is that the jerk function must be finite across the entire interval. So turning our attention back to the fundamental law, when we talk about the first and the second derivative, what we're talking about there is the velocity and the acceleration, because the velocity is going to be our first derivative and the acceleration is going to be our second derivative. So the function that we see once we take our first derivative and then our second derivative, both of those results must be continuous if our CAM design is going to be adequate. Otherwise, we're going to end up with discontinuities and infinite jerk, which is our corollary. And so what we're going to do is we're going to move forward and focus on the idea that as we look at our position graph, we're going to be trying to find a function that results in the velocity and the acceleration graph being continuous over the entire 360-degree interval. So we need to piece together functions which behave better than the linear function which we used in the previous set of slides. Let's try something called the simple harmonic function, or a simple harmonic motion which uses a sine curve for the rise. And so for this function here, we're given a position which is h over 2, where the h is related to the height that we want to rise. And then we have it multiplied by 1 minus cosine pi theta over beta. Now we're going to focus a little bit more on some of these variables in a second, but let's just say for now that the theta in our numerator is the CAM position and beta is the width of the particular part of this function. And so if we go back a few slides, again to our position curve, what we'll see, actually let me go back to this one. So what we'll see here is that the theta runs along this direction for our CAM angle, that's our theta, and beta relates to the particular part of the curve that we're currently in. So the low dwell has a beta of 90. The rise is going to also have a beta of 90 because it goes from 90 to 180. The high dwell has a beta also of 90, and the fall in this case has a beta of 90. So all of our betas are 90 in this case. This does not always have to be the way that it is. Just so it is that way for this particular example. And so here we have a function for our position. It is equal to the following, and we can differentiate this position and get velocity. We can differentiate this velocity and get acceleration. And again, we can differentiate this acceleration equation and get jerk. The only value that is a function that is not constant as we do this is our theta. So every one of these derivatives is with respect to theta. And so now we have position, velocity, acceleration, and jerk, and we could plot them all, and then of course we'll be looking to see that this does not invalidate our fundamental law of CAM design, which means our velocity and acceleration profiles must be continuous for the entire duration, and our jerk profile must be non-infinite, or it must not ever become infinite. It's got to be finite across the entire interval. And so here we see some curves. So we've plotted our position curve, our velocity curve, our acceleration curve, and our jerk curve. So right away, instead of a straight line for our position curve, now we have a kind of this nice S-type curve here. And you see what our velocity looks like and our acceleration. But look at this here. Our acceleration is not continuous at the beginning or the end of the interval, meaning that our second derivative is not continuous. So right away we know we have violated the fundamental law of CAM design and its corollary also, because our jerk is not finite. It is again infinite because of the quick step up that we have for our acceleration. So we still get an infinite jerk when we match up to the dwell regions. So we need to get the acceleration to be 0 at the ends of the rise interval. And so when we look at this here, if our acceleration had been 0 here and had then gone up come down, and then closed here, we wouldn't have this instantaneous jump in acceleration, and therefore our acceleration would be continuous and our jerk would be finite. And so we're going to need to modify our function. This is the sine curve as shown is also not a valid it's not a valid way to design our cam. So we're going to try something called cycloidal displacement. And so for each one of these, what you'll see is we get different equations for our position, which of course is differentiated to give us velocity, acceleration, and jerk. In this particular case, you can see that it looks a little bit different than our equation looked before. You can see our same variables as we had before. We have betas, we have a height h, and we have a theta. And we're going to plot these and see if indeed the velocity and the acceleration are continuous throughout our motion. And so in this case, we see our position curve still looks very much like an S, not very much different than the one we saw before, which is a simple sine curve. We have our velocity, and notice this time our acceleration curve does start at 0, and then it goes up, it comes back down, and then you see we have a jerk. And so look, we have what looks like to be continuous for both of these two guys, but our jerk is also finite. It is not infinite in this case. So it looks like this may be a solution. So we can use similar functions for our fall region. Now, what we're saying there is that this gets us from our low point to our high point. And so if our valve and our engine started closed, then it rose. Now it's open and it's going to dwell again. And so this was a rise function. We can do the same thing for our fall. We simply need the inverse of each one of these. So we can use similar functions for the fall. And so this is where we show both of them. So here's our rise function for position, velocity, acceleration, and jerk. And then we have our fall functions. And so for the fall, we have a starting at h, right? And so before, when we were rising, we went from 0 to h. Then we're going to dwell, and then we're going to need to fall. And so we're going to start at h and then come back to 0. And so if we look at our function here, we start at h when theta is equal to 0. This will be gone. This will be gone. So we're starting at h for our position, and then we're going to fall. And so these are our fall functions, okay? And these are our rise functions, right? And so here we see position, velocity, acceleration, and jerk for the rise, position, velocity, acceleration, and jerk for the fall. And so this is what our fall equations look like. And we see that we have a successful relationship for this particular example because we don't have discontinuities in our first or second derivative. Now we're going to look at something called a combined function. And this combined function, the first thing that we're going to look at is a constant acceleration. And this is just another example of cam design. Again, in this particular case, we're looking at something that is often called bang bang, where we get a maximum acceleration, the maximum that we can get for a period of time, and then a maximum deceleration for a period of time, which is going to get us from our low point to our high point. And so again, remember that when we start off, we're starting off at a dwell. Our valve is closed, it's just sitting there, and then we need to get up to a rise point. And so what we're going to do in this case is we're going to get maximum acceleration, which is going to get us moving very fast, and then we're going to get maximum deceleration, which is going to bring us back to 0 in terms of our acceleration and in terms of our velocity, so we're ready to dwell. Now, there's a problem if we use this acceleration profile. This acceleration profile will result in a fast-moving valve, and then it will decelerate it to 0. So that's great. However, it's not continuous at these locations. So it ends up giving us an infinite jerk, which is the corollary to our fundamental law. So this fails in two ways, right? It fails in terms of not being continuous in the second derivative and for not having finite jerk. And so what we need to do is break this up so that it's not discontinuous at these locations. And so we can do that in this manner. So what we're going to do is we're going to, instead of having it come straight up and over, we're going to have it kind of go up here at kind of a little bit less, not directly up, but we're going to have it kind of slope up in this form. Now, since it's not immediately going up, it's going to need to do that for a longer period of time. So that's why we see the acceleration now is actually higher than it previously was. And then it's going to go down again and then over and then back up. And so now when you look at this profile, we see that in this particular case, we end up with jerks that are they are finite in this case. So what we can do here is say that even though our jerk here is not infinite, it is very discontinuous. And what we say is that the discontinuity in our jerk tends to create a vibratory behavior in gears or other transmission elements connected to the follower in this case. And so really even though this is it's a valid jerk profile, we don't want to use this because it's going to really cause some problems in our engine. It's going to be there's going to be a lot of vibration associated with it. And so what we're going to do is we're going to modify that trapezoidal acceleration so we'll get a less ragged jerk. And the way we do that is taking a sine wave and splitting it apart. And so we're taking this sine wave and we're going to split it apart, and we're going to kind of use both pieces of this to create our acceleration profile. So now instead of just having this acceleration that went directly up with a straight line, now we kind of have a smoother acceleration, and then we'll go over constant here, and then we'll have a smooth one down, whereas before we had a straight line. Okay, just to refresh your memory, we had a line here that was straight, whereas now we're going to kind of have a smooth curve on that acceleration. And so if we look here, we've taken that acceleration, which was maximum up and then maximum deceleration, and we've put these smoothed edges on it. And so now we have this, what we call a modified trapezoidal acceleration. And it's going to result in a less ragged jerk function. Here's a plot of what we'll see for the rise on our position curve when we use this modified trapezoidal, our velocity curve. We built our acceleration, so you've seen it before. Right? We have these curved portions here and flat portions here, and look at that jerk. So our jerk here is still not it's not infinite, it's a finite jerk, and it's smooth. So instead of getting these kind of breaks that we had before, these kind of rough, ragged jerks, we get a smooth jerk profile. So the modified trapezoid is also one that does work for us. It is continuous through our first and second derivative, and it has a finite jerk. Here's another design that works. It is a modified sinusoidal. It has a better jerk, a higher peak acceleration, but a lower peak velocity. Okay, we start off with a similar sine function, and then we break it, we transform it as follows, kind of blend it out, where we kind of stretched it out in a way to where we no longer have this straight portion on our acceleration. Okay, and so when we look at it here, we've broken this apart. We've taken this acceleration curve and kind of spread it out as you see here. And so we're just taking the first beginning of that acceleration, and then we're taking this middle portion and kind of fitting it in here. And so we end up with this profile on our acceleration. Okay, and so our acceleration profile is a little different than it was in the modified trapezoidal. And the result, actually I don't have the result to show you on the next slide. What we do show is all the acceleration profiles that we've seen. Okay, so we'll see both this one, which is our modified sinusoidal, and so you see it here in black. That's our modified sinusoidal acceleration. You see the modified trapezoidal acceleration right here, the one that's the solid line. We see also some ones that we haven't talked about yet. We have the polynomial displacement, a 4, 5, 6, 7 polynomial, a 3, 4, 5 polynomial. We'll focus on these types later on, and of course our cycloidal displacement, which was our sine acceleration, which we also saw. These are the jerk profiles for each one of those. Notice that they are all finite. We have our velocity profile. It is continuous. One thing to note here is that the modified sine has the smallest velocity of all of them. and of course our S, our displacement curve. Notice our displacement curves are almost exactly identical. The modified sine, modified trapezoid, cycloidal, they're all sitting right there on top of each other. Even though our velocity profiles, they differ a lot more, and our jerk profiles and our acceleration profiles are quite a bit different. And so really, when you look at these different designs, you won't see much difference in terms of the displacement, right? They all go from some low period to some high period. However, once you start looking at things like the velocity, the jerk, and the acceleration, you see quite a bit of difference. And that's the end of our introduction to CAM design.